Hello, my name is Brianna Durso, and I'm going to be presenting on some basic concepts of electronics in the context of a few specific applications. So, I'm going to start by going over the basics of electrical potential, otherwise known as voltage, as well as current and its relation to voltage. I'll also be going over an example application of voltage and current in the context of a project, which will be used as the basis for all of the examples shown throughout the duration of this presentation, which I'll be referring to as the portable terminal. Terminal as in the computer sciencey sort of thing that you can run commands on. After that, I'm going to also, I want to mention I apologize if my voice sounds weird or anything. I'm currently sick at the moment. But anyways, after that, I'm going to go into what circuits are, as well as a couple of the more foundational electrical components that are commonly used in circuits. The example for this section will be the battery charging board, which is a component of the portable terminal. I'll then be going over what PCBs are, how they differ from traditional circuits, as exemplified by the Raspberry Pi 02W, and lastly, I'll be discussing integrated circuits, as exemplified by the CPU utilized in the Raspberry Pi 02W, followed by a conclusive review of the presentation. So, electrical potential and current, what are they? A differential in electrical potential, commonly referred to as voltage, is a measure of the difference in electric potential energy per unit charge. It is analogous to the electromotive force, or EMF for short, which is essentially the energy produced per unit charge. The relationship between the EMF and the electrical potential differential can be seen as analogous to the relationship between kinetic and potential energy. Current, on the other hand, is the amount of charge per unit time, usually seconds, which flows through a given area. The two of these phenomena may be used for a very diverse array of applications, generally in the form of circuits. When a full path exists between the positive and negative terminals of a source of EMF, as in a path from high potential to low potential, and electrical current is produced along that path. This path is known as a circuit. The electrical current is able to do work within the circuit and can be utilized in all sorts of applications, from the generation of visible light through resistive heating to advanced circuitry like the stuff in your computer. Different levels of voltage and different levels of current behave differently in different materials. Thus comes the balancing act, which is a necessity in the production of useful devices which use these phenomena. If voltage and current levels are not considered properly in the design of a circuit, the device can go haywire, which can result in a wide array of things that you don't want to happen, from lithium fires to melted or broken components. As an example application of voltage and current, I've put together a basic portable terminal using some basic off-the-shelf electronics components. This is essentially a little computer running a desktop operating system and has been designed to be highly portable, and the involved circuitry consists entirely of direct current or DC devices and EMF sources, those being the battery and a charger. Several PCBs have been wired together in order to facilitate communications and operation of the device. One of these is a basic TFT display, which is controlled by the Raspberry Pi 02W single-board computer via a serial peripheral interface, or SPI. The purpose of this device is for use interfacing with other more powerful computers for things like managing computationally intensive processes running in the background or general systems administration. Now, circuits, as previously discussed and described, are in their most basic form a simple path from high electrical potential to low electrical potential. These paths can be made much more complicated in order to perform more complex tasks like turning on a light or calculating the nth digit of pi. These circuits are often composed of a diverse array of components. However, two of the most common and most fundamental of those is the resistor and the capacitor. Resistors are components which are inserted into a circuit in order to deliberately increase the resistance at a specific part in the current path. This is often done in order to take advantage of the relationship described by Ohm's law, such as decreasing the flow of current or voltage at a specific point in the circuit. Ohm's law is the V equals IR in the corner, which means voltage equals current times resistance, where voltage is V, current is I, and resistance is R. This is able to be done because of the resistance of the resistor, which is also how the magnitude of the effect of these adjustments is able to be managed and controlled and fine-tuned. Resistance is essentially a measure of how difficult it is for electrons to pass through, or rather along the surface of, a conductive material, such as wire or a battery, each of which have their own resistances. Capacitors, on the other hand, are components which can store electrical charge and energy and expel it later at a rapid rate. Capacitors are useful for a lot of things, such as filtering noise in a signal or limiting the voltage delivered to a specific part of a circuit. The amount of charge a capacitor can store relative to the electrical potential differential between the two opposing conductors of which the capacitor is composed is the quantity known as capacitance, which is more particularly a measure of the amount of charge per volt that a capacitor can store. So, as an example used for circuits and resistors and capacitors, I'd like to highlight the battery charger module, which was used in the construction of the portable terminal. This component is used to charge a battery via USB-C and can output a 5-volt signal of up to 500 milliamps for use by other electrical circuits. Resistors and capacitors, alongside an integrated circuit and some standardized adapter plugs for external electrical connections to be made, are used by this module to facilitate the manipulation of the level of voltage and amperage which goes where in the circuit. For example, it is with the aforementioned components that the circuit charges the battery without damaging it, without the need for intervention from the user. Printed circuit boards, or PCBs for short, are essentially pieces of fiberglass or some other insulator that have been etched and or had one or more layers of conductive material, such as copper, deposed onto it for use in the construction of circuits. PCBs are often used for the miniaturization of circuits as well as for making them more robust, and can be found in all sorts of things, from refrigerators to phones to cars to computers. A popular example circuit board is the Raspberry Pi 02W. This device is very versatile. It's cheap, has decent computational performance in a small package, and has some fairly robust GPIO, or general purpose input-output, neatly packaged into a single board computer, or SBC, which is capable of taking on a very wide range of applications. PCBs are relatively straightforward to automate the production of in today's world, especially with the use of SMD or surface mount device components. Excuse me. And such means enable the mass production of boards like these for their use all over the world. In the context of the portable terminal, this device serves as the center of all operations, a central processing unit, if you will. It runs the Arch Linux operating system, which is running firmware set up to display video to a display via SPI, serial peripheral interface, and can connect with many other devices through its added STEMMA QT I2C connector, the red thing in the top left corner of the picture on the right. A device like the Raspberry Pi 02W, however, would not be possible if it weren't for integrated circuits, or ICs. ICs, much like PCBs, are circuits which can be created through patterns produced by means of photolithography via the use of photosensitive chemicals. Unlike PCBs, however, ICs are able to get feature sizes on the order of microns or even several nanometers in some circumstances. How can this be done? Through the use of silicon substrate, advanced optics technology, a good bit of chemistry, and a whole lot of other means for producing layered amalgamations of electronics components, which can sometimes look like nano-sized cities. ICs can be used for all sorts of things, from the central processing units or CPUs in your phones to MEMS devices, micro-electromechanical systems that can be used for things like COVID tests, and also in your phones for things like gyroscopes and accelerometers. For example, the IC that's at the center of the Portable Terminal project consists of what's commonly known as a system on a chip, or SoC for short. In this case, that system on a chip is composed of a quad-core 64-bit ARM Cortex-A53 processor running at a clock speed of 1 gigahertz, which means that it can run approximately 1 billion operations per second. This CPU is joined by 512 megabytes of SDRAM, as well as a bunch of connections and managing circuitry to facilitate the control of the GPIO pins used to communicate with other devices. So what have we learned here today? We've discussed electric potential and current, and how potential differential causes current to run through a circuit, enabling the extraction of useful work from its constituent components. We've discussed circuits, what they are, how they can be used, as well as what resistors and capacitors are, and how they work and can be used. We've discussed PCBs, some use cases, why they exist, how useful they are, and we've discussed ICs, and how they are similar to PCBs and are the central node around which the newly digitized world revolves. And with that, I'd like to conclude my presentation on the basics of electronics and their applications. Thank you for your time.